Now we're going to look at electric fields near point charges. Concept 0 is, let's just talk about the direction. If you have a positive charge, then the electric field is always going to be away from that charge. If we put any positive charge anywhere near this guy, it would always go away. And the opposite is true for a negative charge. If we put a positive charge here, it'll always be toward the negative charge. Okay? Because remember, it's what would positive charge do. That determines the direction of the electric field. Okay? So here's a little diagram here, right? Here's a positive charge, and this electric field at this point here, these are not charges, these are just locations with nothing there. This electric field is large and away from it, straight up. This one is a little bit smaller because it's farther away, right? But it's directly away from it, right? And then this one's even farther away, so it's even less, but it's always away from it, okay? Now, the formula for this, let's just derive that, right? Remember that electric field is force divided by charge. Well, the force is equal to KQQ over R squared. And then we're going to divide that by a charge, right? I'm using Coulomb's law here. And so electric field is it's kind of like the sound of one hand clapping, right? There's just one charge, and then it's the notion that if we have this charge here, what would be the force per unit charge if there were another charge there, right? So it's very abstract and bizarre thing, right? We're talking about the ability of that space to exert a force on the charge due to this charge right here. Okay, so our formula is electric field near a point charge is KQ over R squared. And now the equivalent formula for gravity is G is equal to, this is the gravitational field strength, right, is G M over R squared. Okay, so two different formulas. This is for electricity, this is for gravity, right? This is easy, it's always toward the mass. This one's a little more difficult. It's away from positive charge toward negative charge. Okay, let me do an example here. Okay, so 2 meters to the right of a negative charge here. So here's this negative charge, right? 21 microcoulombs. So 21 times 10 to the minus 6th coulombs, right? And then we're like right here, right? Okay, we're 2 meters. Okay. Well, first off, the electric field's going to be to the left. Okay, if we're right here, if we're here to the right of it, it's going to be toward that charge, because that's what positive charge would do, is go toward that charge. So that's how we get the direction. And now we can use our formula. E is KQ over R squared, right? So it's going to be 8.99 E9 Newton meters squared per Coulomb squared, right? I'll throw the units in for this example. And then 21, I'll say negative 21 times 10 to the minus 6th, that's coulombs, right? And then we're going to divide by 2.0 meters squared. Okay, notice that the meters squared will go the way of the bison. One of the coulombs will cancel, and we'll get newtons per coulomb as our units. Okay, so 8.99 E9 times negative 21 E minus 6. I usually ignore, by the way, the minus signs here. I'm just going to throw it in just for kicks here. Divided by 2 squared. And I get 4719.7.5 newtons, and that's negative per coulomb, right? Is that what I get? That is what I get. Okay, and then I guess I rounded it because of sig figs, but there it is. What negative means in this case, if you want to really know, is it really, the electric field should be away. By default, this should be a positive charge, right? So this is negative away. It's negative away, or toward. Do you say toward or towards? I don't know. Toward the charge. Toward, not fromward. If you can say toward, can you say fromward? Away. Now I'm wasting your time. I'm so sorry.